So we got a question from participants about the k-fold cross-validation. So this k means how we split the original data set into different fold. For example, if we have 5-fold, we will split data set into 5 portion, and we train with for example, for first fold, we train with the first portion and test with the last one. Okay, so how's everyone's progress? Have you finished running this one? Okay, we've had a very long session, I think more than almost an hour. So let's have a short break. So if you haven't finished running the notebook too, you may use this time, or otherwise you can relax. Okay. So we got a question from the participants about getting error of the utils. So to import the utils package, you need to make sure that the notebook is under the same directory. For example, for me, it will be the hands-on with this util package, util function. And we use this util, I think, for the masking. So if it constantly not working for you, you may like only evaluate with the full data set, a testing data set, without manually create the missing values. And you can explore these later. Alternatively, you may like copy everything from this util function and pass it to this notebook and run them. So you don't have to import everything from this utils package. Okay. So we have mentioned the dataset description. We have also checked the machine learning based methods based discriminative and generative classifiers. Now let's focus on the deep learning based discriminative model. So first, let's have a look at a relatively easier model compared with others. So the fully connected layer based classification. So I'm sure most of you are familiar with this fully connected layer. So I put the picture here just to make sure just to make sure like the name aligns with the one like along with the picture over here. So the fully connected layer sometimes also refer to maybe multi-layer. I think the ANN or other terms like all connected layer. So things like that. It has like inputs and outputs, which you need to like customize your own dimension, and all the neurons between these input and outputs are connected. So for implement the fully connected layer in PyTorch, we are going to use this torch.nn.linear, which is the PyTorch inbuilt method for this fully connected layer. And the essential arguments are the input dimension and output dimension. Also, whether you are going to use a bias term, for example, this b plus b over here. And as for the input dimension, it should align with the input feature argument which you define. And for the output, it will generate the output dimension as you defined of this linear model. We are also going to do the optimization with this PyTorch AutoGrid. So here is just one diagram to show how this optimization happen. Essentially, it following this chain rule of optimization. For example, this figure gives a toy example of calculating log xy. So for PyTorch, it will store a value for each operation. For example, this V stands for the x times y, and then the log calculation. After that, we obtain this W. For the backward propagation, it happened backward. So which means it will initially calculate log derivative regarding this V, and after that it will calculate the derivatives regarding this x and y. And as you will see in the code, it's quite straightforward and easily to be implemented. So if you have further questions regarding this AutoGrid, you can check this blog. So we have understood basic concepts of this fully connected layer. Let's check about the fully connected neural network model and also optimization of the discriminative classification model. Three FCN classifier. So for notebook 3 to 6, we are going to work on deep learning model. notebook 3 and 3, 4, 5 are discriminative model, and 6 is for generative classifier. And for all these discriminative classifiers, they basically share the structure. So I will go through these notebook 3, and for the notebook 4 and 5, they follow the same structure, so we can quickly check it. So for this notebook 3, again, at the beginning, we import all the necessary library. Essentially, we will need this Torch library, Torch framework for deep learning, and also maybe scikit-learn for splitting the training and the testing as we did for the machine learning models. So here is the data preparation for the deep learning models. It basically very similar to the one we have seen in the machine learning in notebook 2. And the output will be the sublated training and the testing data set for both the input, which are X train and X test, and output Y train and Y test. So following that, we also perform this data preparation for either under sampling, over sampling, or we keep the current format. And we define certain terms, for example, the dataset name, number of temporal features, statics, and the number of time steps, which we have covered in notebook 1. So if you run this train test split function, you will obtain the train loader and the test loader. So the idea is in deep learning, because we perform the stochastic gradient descent. So for each batch, we will sample certain instances from this dataset. And for this data loader from the PyTorch, it can iteratively generate the batch of the training data or testing data for us. So feel free to check this function about how to split them in and convert into the data loader. And this is the fully connected FCN model we are going to use. So that will be the define of the model and also the forward path of the training about how we obtain the final label. So I will skip this block right now and focus on the backward path, which shared for most of the notebooks. And we will check this FCN layer later. And for block 5, so over here, we define this model, which is actually the previous block with certain arguments, which we will cover later. And essentially here, you need to specify the device you are using. So if you are if you are using Colab, you need to change this to either CPU, or you need to change it to GPU if you want to use the GPU resources. So for me, I'm using Mac, so that's why it's MPS. Next, we define this optimizer. We are going to use this ADAM optimizer, but feel free to change it to, for example, SGD and or the RM prompt, so things like that. So this ADAM optimizer will optimize the parameters for the model we have defined, which will be the FCN model in this notebook. And for this ADAM optimizer, we need to set the learning rate. And here we use a relatively small learning rate to train the dataset. And finally, for this block, we define these criteria, which will be the cross entropy loss to calculate the loss. And the loss will be used to optimize each neuron within this forward path. So alternatively, you can use binary cross entropy loss, but here we basically treat it as a classification task with 2 targets, either 0 or 1. If you use binary cross entropy loss, the output will be 1. If it's above 0.5, then positive, otherwise negative. And here again is similar to notebook 2, here we will manually create the percentage of missing values for this temporal modality. With certain percentage of missing values for the testing purpose. And the reason we forward this number of time steps and type steps into this feature is to reshape it later, as you will check these mask times within that util function. So once we generate this mask, we will replace the place with mask to 0, to -1. So we treat them as missing values for the temporal modality. And the callback of this function is the masked temporal data for the testing data set. And let's have a look at training with PyTorch. So this function of train model defines how we are going to train the model. So we need to define the number of epochs. So this is a hyperparameter, like after certain epochs, we will stop the training. Otherwise, it will maybe go forever, and we don't want to do that. So for this print after iter's, so here I didn't use it. The purpose of this function is to check the training performance within the epoch, or like to monitoring the current training performance. And we will store the loss of the training and accuracy of the training throughout these kind of, I think, epochs. And here, so we set the model which we defined over there, the FCN model, into the training mode to allow the to allow the gradient calculation of the PyTorch. So this step is very important. As you can see in the evaluation step, we'll set it to evaluation mode. So for this training mode, aside from the enable of this gradient calculation, it also enable other functions. For example, dropout, which you will randomly drop certain percentage of the neurons, or deactivate certain percentage of the neurons in the forward path. And in the evaluation path, it will not drop. It will like deactivate that dropout function, unless you manually set it. So here we have two loops. For the outer loop, we iterative over the epochs. For each epoch, we are going to go through the data set. And for this inner epoch, we obtain the temporal and the static information, as long as the label information from this train data loader, which is the train loader. So the first step you are going to do if you work on, for example, GPU, is that you are going to load these temporal and static feature to the GPU, which through this .to device function. So this device is what you define over here. So if you are going to work on GPU, you need to, oh, sorry, not GPU. You are going to use, for example, CUDA. Or you can simply just run it with the CPU. So you comment out this line. And at the beginning, we set the gradients for optimizer to 0. So that is to prevent the gradient accumulation throughout the training. And because we don't have our data set is not that large, and we don't use some function like the contrastive loss, so we don't have to use a very large batch set to accumulate these gradients. So we simply like zero out all the gradients for each iteration. So iteration means each batch over here. One possible usage of not zeroing out this zero gradient is in contrastive loss, when you only have a very small sized GPU, for example, only 1 gigabyte. But for certain algorithms like the contrastive learning, you have to train it with a relatively large batch size. In that case, you can accumulate your gradients for certain iteration or certain batch, and then you conducted the gradient you update the gradients. So that's how how people doing with these zero gradients. And within this line, we perform the forward pass. So the input will be the temporal and the static features. The output will be this y hat, which is the prediction made by the FCN model or other models in the later notebook. So we send these results to CPU, calculate the loss between this y hat and y. So that's how we calculate the cross entropy loss just through this line. And next, we calculate the gradients for each neuron through this backward function. So this backward function will follow that backward path, which I just showed in the slides. So following that computational graph and generate the gradients for each neuron or each layer. And following that, the optimizer.step. So over here, it will actually perform the optimization toward the neuron. So the difference is for this backward, we only calculate the gradients. We haven't update the parameters. So the parameters will stay there. Only after these step, we update the parameters value and finish the optimization of this iteration. And next, we calculate the accuracy of this batch, and calculate the accuracy score. Again, it's just for monitoring throughout the training, and once we iterative over the inner and outer loop, the training has been done, you will get an updated model. So we will pass this loss item, accuracy, and also the trained model back to the main function. So for the evaluation, again, this is shared by most of the notebooks for deep learning method. So similar as the notebook 2, we just run. So we will manually create a certain percentage of these missing values throughout this masking function. And while testing, we forward this masked temporal modality and the static modality to this model, which has been trained. And we calculate their loss and also the other criteria like the accuracy, precision, and so on. And importantly, while we do the evaluation for this PyTorch framework, we need to set this model to the evaluation mode. We also need to, we usually do that like the with torch.no gradient, which means we don't need the optimizer to calculate the gradients for our model, just in case it's updated according to the testing data, which will cause this, the label leakage problem. Okay. So for the min path is just running this train model function and also do the evaluation, and you will get this result. So that is the backward propagation or the optimization of these discriminative models using deep learning methods. Now let's focus on the forward path. So for this FCN model, we need to define, like we just saw in the slide, like the input dimension, output dimension. So for us, the input dimension will be the number of statics plus the number of temporal modalities times the time steps. So as you may notice, so in that way, for the fully connected layer, it will take all the features as input without the splitting of the temporal or the static modality. So we basically do the same thing as the notebook 2 about handling this longitudinal data. And you need to manually define this hidden dimension, which we currently in this notebook, I think we set it as 64, but you can modify it maybe to other values. And finally, the output dimension will be the number of classes you are going to use for classification. For us, it will be 2 because we only have 2 labels, either drop or not drop. And then we define each layer over here. So here we have 3 layers. So FC1, FC2, FC3. So along with these layers, we also define this batch normalization to stabilize the training. And here are some methods to initialize the FC1 and also maybe set the bias at the beginning layer to 0. So those are just empirical settings. You can also ignore these 2 lines if you don't think they are that useful in your case. And for the activation function of the fully connected layer, we are using this leaky rulu with a 0.2, I think. So it's kind of the hyperparameter decide how leaky your activation will be. So if you don't have any value over here, it will be identical, I think, to the standard rulu, which means for all the negative values, it will generate 0. And finally, we have the softmax function. So it will help us generate the prediction confidence for the output layer, which will be this final layer. So those are the definitions of all the layers. Now let's just stack them together to generate the forward path of the deep learning model. So for the deep learning, for the forward path, it will take the temporal and the static modality as input. And we will get the batch sets from the temporal modality shape 0. So because we are doing batch normalization, it will have 3 dimensions. The first one will be the batch sets. The others will be dimensions, for example, the temporal modalities or the static modality. So here we flatten the temporal modality because as we mentioned over here, we are going to treat all the variables equally without considering these kind of temporal dependencies between variables. And we concatenate the temporal and the static modality altogether. So in other words, we will get something very similar to the original CSV file. So the reason we keep reshaping is because we want to make this code more generalizable to, for example, LSTM and FCN or the GAN model over here. So that's why we reshape and concatenate all together within this notebook. And we will perform different layers like FC1, FC2, and FC3. And finally, the output layer. And you will get the output of the final layer, which will be the prediction confidence for each instance. Okay, so after running this main function, you are going to obtain something like this. So it will indicate the training accuracy and also proportion of missing values, the accuracy of this model, and also precision recall F1, and also the different criteria. Because it performs multiple fold, that's why we keep getting results iteratively. So if you set that key fold to a very small value, so you can split it with less fold. So things like that. And now I will pause here, and you may have 10 minutes to run this notebook to check its performance. So this device depends on the system you are using and also the computing resources you are currently using. If you are running it on CPU, just change the device name to CPU. And if you are using GPU, change this device name to CUDA. Alternatively, if you are using mic system, you can change it to MPS. How's everyone going with this notebook 3 about using fully connected layers? Do you need more time on running this notebook 3? Okay, that's good. So I just realized we only have approximately 45 minutes left. I will skip these LSTM-based, so here, I will skip these LSTM-based discriminative model and also the CNN-based model. But all these slides and the notebook are provided, so please check it after this tutorial. So right now, let's directly jump into the scan-based method. So because we are going to mention the scan-based method, like the theoretical series about the scan and how it works theoretically next week. So here I will only briefly discuss how we are going to use scan for classification for our notebook 6. So here is the model we are going to use. And so in general, GAN has two networks, the generator and the discriminator. The generator will try, sorry. So the generator will generate the, generator will take the noise, for example, from certain from certain distribution as the input, and then manage to generate a data, generate something, for example, vector as similar as the raw data as possible. For example, for us, the longitudinal samples will be, the ESL dataset will be longitudinal samples. The generator aims to generate some data similar to the the temporal feature we've just seen over here. And from the literature, most of the works of this temporal classification will ignore this statistical modality. But here we are going to utilize it especially in the discriminator part for the prediction. And also, I forgot if we include these for the generation or not. We will check the notebook later. And the second part of this GAN model is this discriminator. Its objective is to check if the thing generated by this generator is real or not. So it will take this as the input and predict if it is real or fake. It will also take the raw data, the original input data as the input and predict the real or fake. The ultimate goal when it converges is that the discriminator cannot tell if a instance is from the generator or from this original data set. So this GAN has been used in the image and also other domains. And here we are going to use it in the longitudinal data. So for the data set, for the model, we are going to explore because we are going to do the classification on top of the original GAN model with discriminator and the generator. For this generator, it has a subtask of the classification. So as it indicated over here, the discriminator will have task 1, which aims to predict if a sentence is real or fake. It will at the same time predict if this input instance belongs to, for example, not dropping or dropping. And our overall loss are something like this, as it illustrated on the right-hand side of this screen. So essentially, we have 3 losses. So the first loss is for these. So the first loss. I think. Yeah, for the last one, I think it is for the discriminator for the prediction loss is over here. So this one. And for the middle one over here is for the generator, which aims to which is the adversarial loss, which is real or fake over here. And the first line over here is for this discriminator, which aims to predict the generated results are either from the samples or from the real one. So that's the idea of the GAN-based method. And now let's check notebook 6 about how to implement the GAN method. It's a little bit more complicated than the 3, but I will go through it. Hopefully it's not too confusing. Okay. So the first block, I think, is similar to notebook 3. The only difference is that we import this low-GAN LSTM, CNN, FCN, which are different kind of backbone methods for the generator and the discriminator. And again, we have the same block of this data preparation. We will also define this kind of the number of steps, like the parameters for the training. And here is how we actually perform this prepare the data set with this function. And that is the dimension of our input. So it will have, I think, 75 variables. Okay. So here you have 3 options for the generator and the discriminator. Either you are going to use these LSTM, which are these 2 lines, or you can use a CNN-based generator or discriminator. And alternatively, you can choose this fully connected layer based generator and the discriminator. So currently it is using this LSTM. And another difference between this generative classifier and the discriminative classifier is that we define these 2 optimizers. So this G-optim aims to optimize only the generator part. So as you can see, the parameters only include the generator. For the discriminator, it will only include this discriminator part. And we will have a look of this generator and the discriminator just to show you how it works to get the results. So I think because we already skipped this LSTM and CNN, we will run with this FCN. Sorry. And if you go to this low-GAN FCN, you can see how the generator and the discriminator are structured. So for this generator, it's very similar to the previous one. The only difference is, I think, the output dimension. So we will not output only 2. The output dimension will no longer be 2, which is the number of the classes. It will generate a much higher dimension, which is identical to this out dimension here, which is identical to the temporal features. So it will be the number of time steps times the number of temporal features. So again, we use the generator to generate the to mimic this temporal modality only in this notebook. But in your case, you may generate it for other maybe modalities. So that's one difference. The output will have a higher dimension, which is identical to the temporal modality. We will reshape it because if you use the fully connected layer, the output will still be a vector, and we need to reshape it to the same format as the input data as we did for the true data. As for this discriminator, it will take, so for the forward pass, it takes the temporal and the static features as input, it will perform basically similar things as the FC layers we've seen in previous notebook, which is notebook 3. The only difference is that it on this line 74, it generates the adversarial results. Like the goal is to predict if the instance is real or fake. And then we will generate the confidence of the prediction. So in other words, these two headers correspond with the two tasks of the discriminator. One is to judge if the adversarial laws of judging the true of real or fake, and the classification task will share the same like representations. And the return value or the callback of these function would be the probability for the two tasks respectively. So this one will be the adversarial, the confidence for the adversarial task, and also for the auxiliary task here, which here means the classification task. So that is the discriminator and also the generator. Basically, they have the same structure as the FCM model we've seen in notebook 3. And so those two networks are optimized with their own criteria. Here we use the BCE laws to optimize the auxiliary, the adversarial learning task. And we use these cross-entropy laws to optimize the classification task. So throughout this notebook, I think the auxiliary means the classification because it's kind of an auxiliary task for the generative adversarial network. So again, we will manually create certain percentage of the missing values using this kind of function, similar as the previous notebooks. And this block indicate how we train the generator. So the input will be the temporal and the static modalities. Again, for the generator optimizer, we set it to 0. We set the gradients to 0. And here we define the labels for this adversarial task, which aims to predict if the instance is from the generator or from the raw data. And that's why we have 1 for these, we will have 1 for the real data and 0 for the generated data. That's why we define these two variables over here. So basically, it's all either O1s or O0s with the same dimension as the temporal modality. And you may need to set these required gradients as false. Next, we will, this is the input for the generator, which will be some noise from with the same format as the temporal modality. So again, for the generator, it takes some noise as a trigger, as input, and it will output an instance which is similar to the distribution as the real data. So that is the purpose of this generator. And you can check the sample data function to see how it generates the this kind of random noise. So we take this random noise as input together with the static modality. So again, for this task, we only use the generator to generate the temporal modality, which is more close to the real world applications, because for most of the time, the demographical information carried by the static modality are available. And we will get the output, which is a fake temporal modality data. This one, together with the static data, will be forwarded to the discriminator. And what we will get are 2 confidence score, one for the discriminative task, one for the auxiliary task, which is the classification. And we will calculate the discriminative loss for the generator according to this valid generated from the discriminator and also the valid labels, which defined over here. And then we will optimize the generator according to these laws and calculate the gradients and also update the generator model. So that's all for training the generator. Next, we will optimize or train the discriminator part. So that's the reason why we have two different optimizers, because the training of these generator and the discriminators are always separate, like using different kind of losses. So again, for this discriminator, we need to predefine the labels for the adversarial loss. We set these optimizers, the gradients of the optimizers to 0. The difference is that here we train with the real data, which is this X tempo, together with the static. And what we will get is the adversarial loss along with the classification loss for this discriminator using these kind of output from the discriminator model. So over here, we forward the real data to the discriminator and calculate its results. Here, we are going to repeat this step for the fake data, which is from the noise generated by this generator. And for other, so the only difference is that for the adversarial loss label, so here is for the valid label. But when we work with the fake data, the label will be the not valid label, which is all 0. So that's, I think, the only difference. Finally, we get all the losses for the discriminator, which are these fake adversarial loss together with the classification loss. And we have a scaling vector over here to adjust the contribution of this auxiliary loss and also the auxiliary loss for classification and also the adversarial loss for the generation. So this beta is a hyperparameter. Once we obtain the loss, we will calculate the gradients and update the discriminator model. Finally, we evaluate the performance according to basically the same structure as previous method. So we will check the accuracy, precision, recall, F1, and so on. And now we have seen how to train the generator and the discriminate, and also so the two networks. So here we assemble them all together and format this training loop. So again, we will go through this train loader, and we will first train this generator. Over here, we will first train this generator, and then we will train this discriminator. And then we obtain all the losses just for the record. And then we obtain the classification performance for this training data set. And here is just to check the loss within, to check the performance within the training, to monitoring the training process, to avoid, for example, you get a very bad, for example, accuracy from throughout the training, then maybe you need to consider change of the hyperparameter. During the testing, so the test phase of this gun is basically identical to the previous, I think, FCN model. So we set these two networks to evaluation mode, and we go through this test loader to obtain the results. So for example, here again, we set this valid label, not valid label, just to make sure it is similar to the previous train things. So we can always check the result of this testing data. And we manually create a certain percentage of these maskings. and we test with the real data first, and then we test with the fake data. So here we want to check how good or how bad the generator performs throughout the training. If the generator performs too bad, probably so the idea of generative classification does not work because of the fail of the generator. And again, we calculate this kind of criteria for the discriminator and also the generator, and we will obtain all the classification results in the following steps. So finally, for the main function is quite similar to the previous notebook. We prepare the data, obtain the training and obtain the input and output. We split the training into certain folds, for example, 3-fold or 5-fold, which are commonly used. And for each fold, we obtain their training, and for each fold, we obtain the training data, testing data, and the labels. And again, we use this function to load them into the data loader of this PyTorch. So here the purpose of this reset weight is at the very beginning, because we train different fold, and this is deep learning. Sometimes the model from the previous fold are still there. So basically we are doing accumulated learning, which is incorrect because each fold should be very independent. So that's the purpose of this one. And finally, we use all the functions we have seen previously to train the generator and the discriminator and evaluate the results according to different proportion of these kind of missing values. And once you run the notebook, so this is a result for using the LSTM as a backbone. If you run it with FCN, you'll probably get different results. Okay, let me try it over here. So it's FCN, and it may take some time to run this GAN model because of this complexity of the generation and the discrimination. Okay, now we get the results. So basically the criteria is identical to the previous one, and you can observe all the results. So as you can see, if there is completely missing for the proposed method, it looks like for the temporal modality, looks like the result is slightly better than the discriminative or the method in notebook 3. So I will stop here and let you run this notebook right now. And again, feel free to change the backbone networks like the generator discriminators to LSTM or CNN. And these kind of LSTM and CNN are basically share the structure from notebook 4 and notebook 5, which we don't have time to cover in this tutorial. So the TQDM module is only for checking the progress of the training, and you can install it, or alternatively, you can delete that part. So it will be basically the similar. We got a question from the participant. So the question is, what is the difference if we select CNN LSTM or FC for generator or discriminator? Like, what impact on performance can be expected and how to decide what to use? So, uh, so, so I don't have time to cover this in this tutorial, but for the longitudinal data, if we trained the static part and also the temporal part, like embedding differently, for example, we use LSTM or CNN method for imputing for extract the features for the temporal modality. Ideally, it can generate a better performance than the fully connected layer, which ignore this kind of dependencies between variables. So for example, for LSTM, it considers these short-term memory concepts. And for CNN, it may generate the, for example, it will calculate do a convolution according to the kernel, which is basically your neighbor, like according to the street size, things like that. Uh, I know most of you haven't finished this training, but due to the time constraint, I think it's a good time to like wrap up right now and summarize this tutorial. So the rest of the code can be treated as a homework, or we have a final session. If you are still interested in this kind of topic of discriminative, generative, and longitudinal data set, we can cover this part in the for the last course. So for this tutorial, we compare the performance of discriminative and generative methods. Essentially, these generative methods, for example, GAN or the Gaussian mixture method, they learn a joint probability between the input and also the label. And conversely, for the discriminative method, it only generated that P, Y given X. So we use GAN as an example, and you may also notice some limitations of using GAN for classification. For example, if you use FCN as a backbone, you may notice that the performance is not as good as you expected because for some time. So we will introduce more advanced GAN models on longitudinal tasks next week. So again, for this tutorial, the experiments and also the code are based on this work. So the authors are Sharon Bashar and also Professor Richie Nayak. So if you find it's useful, feel free to set this work. And in this work, Sharon, so our group proposed a little bit. Actually, it's much more advanced method than the pure GAN for classification as I show in this tutorial. So the idea is while we generate this kind of fake data by using the generator. It's not only just depends on the static and the noise, it also depends on this label information, which can generate much more representations and boost the performance of these classification tasks. And I think that's all for this tutorial. Thanks for your attention, and we will see you tomorrow. So here
Thank you, Dewey.
Yeah.
And this is Dewey's contact and our research group, Advanced Data Science and Machine Learning. So in this today's session, we introduced you to generative models and the associated fields. We showed how generative models perform against the discriminative models. I know some of you wondered that generative models are for generation only, but that is the point we were trying to raise, that yep, advanced generative AI models like LLMs, they are used for generative purposes, and the rest of the modules, we will cover those tasks. But today we wanted to start with slow pace and showing you the simplest tasks that generative models used in classification, and not it's not that we used it first time. They have been used for many decades, but they were not really seen as generative AI models. So it's all good. I think Dewey has gone into much more detail of some notebooks, but some notebooks we had to skip. So please treat it as a homework that would allow you to understand much more of the knowledge and things. So thank you very much. And I hand over it to Professor Namita Mittal now. Thanks, Namita.
Yeah. Thank you so much, Vitri, and thank you, Dwayne. Having lots of efforts, we could see that you had lots of preparation done before. And of course, 2 notebooks are for the homework. And as you requested, I have deleted esl.excel file. That was a private thing. So participants, please note that already you have gone through esl.xls, so it's no more available. And we'll be meeting soon tomorrow, 9 a.m. Indian time, sharp 9 a.m. tomorrow. Hopefully, this time today we are having some technical glitches, so I'm feeling sorry for that inconvenience caused. Thank you so much.
And just one last note, as Namita said that we have removed ESL dataset from the directory. So could I please request participants to delete ESL file and do not use it for any purpose. So that was only for demo purpose, but not for distribution because it's a proprietary dataset. So thanks for your understanding. Thank you then. Yeah. See you tomorrow at 9 then. Bye-bye.
Thank you. All the participants are requested to please leave the meeting so that we can conclude today's meeting. Thank you. Waiting for you for tomorrow's meeting.
So Namita, me and Dewey can drop now?
Yes, thank you.
Okay. Thank you then. Bye-bye.
Bye. It's 9:30 there? 9:30 p.m. there?
1:30.
Oh, really?
Oh, no, right now it's around 8. Around.
Okay, around.
So, do is dinner time.
Bye.
Thanks, Namita. Thank you then. Bye-bye.